Okay, so you already know how to calculate the area of a curved waterplane from your last stability course. It's done using a number of ordinates, which are measurements that are taken at equally spaced intervals along the ship's waterline. The interval, or the distance between the ordinates, is usually expressed by the letter h. Depending on how many ordinates you have been given, you would use Simpson's first, second, or third rule to apply Simpson's multipliers to the ordinates. The end result of the calculation is a number representing the area of the waterplane. Well, the exact same thing can be done to calculate the area under a stability curve and find dynamical stability. After all, a statical stability curve is just another irregularly shaped area, a lot like a waterplane. This time the ordinates are the values for gz on the y-axis, and the interval is the number of degrees between each angle of heel on the x-axis. One difference is that when calculating the area under the curve, the interval between ordinates must be converted from a number in degrees to a number in radians. To do that, divide the number of degrees by 57.3 to get the number in radians. Let's say, for example, that you've got writing levers for every 15 degrees of heel, like this. Because we have a total of 7 ordinates, we can use Simpson's first rule because it is an odd number of ordinates, or Simpson's second rule because the number of ordinates is 4 plus 3. Using the first rule, the gz values are multiplied by the Simpson's multipliers, 1, 4, 2, 4, 2, 4, 1. The products are then added together and multiplied by h over 3. Remember that h is the interval, or the number of degrees between each ordinate. Because there are 15 degrees between each ordinate, the interval is 15 degrees. However, the interval needs to be converted to radians in order to do the calculation properly. So the interval h is 15 degrees divided by 57.3. When everything is calculated out, we find the area under the curve to be 1.88 meter radians. If, for whatever reason, you've got an even number of ordinates, you can always use a combination of Simpson's first rule and the 5/8 rule to find the area. Use Simpson's first rule to calculate the area between the first 5 ordinates, which works out to be about 0.82 meter radians. Then, use Simpson's third rule to calculate the area between the last 2 ordinates using a third adjacent ordinate, which works out to be approximately 0.16 meter radians. The last thing to do is to add the 2 areas together to get the total area under the curve. Sometimes, writing levers are not given at equally spaced intervals. This curve is showing ordinates at an interval of 10 degrees. But what would happen if we were to add an ordinate at 5 degrees? This is often done to make sure that the finer ends of the curve are accurately represented. This ordinate is said to be at a half interval because it splits the regular interval of 10 degrees in half. Here's another example. This table has gz values for 0, 5, and 10 degrees, and then every 10 degrees of heel after that. We could calculate this out separately by finding the area between the first 3 ordinates using 5 degrees as our interval, and then finding the area between the last 5 ordinates using 10 degrees as our interval. But there is a simpler way. Because the first 3 ordinates are measured at half of our interval of 10 degrees, we can take the Simpson's multipliers and divide them in half. Then we can take both sets of multipliers and combine them into one equation. That way we can still calculate our area using the common interval of 10 degrees. Our final equation looks like this. h over 3 times 0.5a plus 2b plus 1.5c plus 4d plus 2e plus 4f plus 1g. When doing calculations using Simpson's rules, it's extremely helpful to take your time and write out as much of your work as possible. Don't worry about wasting paper, and don't hesitate to draw a diagram or table to keep yourself organized. Write out each step of the calculation to make sure that you don't make any small mistakes.